Hey John, so this is the kind of continuation of the ALU project. Since deciding to start that, I also started to do this thing. It's kind of this online course called NAND2Tetris. I thought it was pretty interesting, and they start to build an ALU in there. So I've kind of I've kind of decided to change things up a bit um, to try to implement their design. It's better. It seems like it's more comprehensive. But just to talk about this NAND2Tetris real quick, it's pretty cool. What they do is they have you build. The idea is that you're gonna build from NAND gates. That's like an AND gate whose output is just inverted. It's a basic universal logic gate. You're gonna take NAND gates. That's like the only building block, one of the few building blocks you start with, and you arrange those to make all the components of a computer, and you put all those together to build the computer. This is all virtual, of course. They have a software package you download, and you kind of run this virtual machine on their thing. But they walk you through Boolean logic, and they walk you through building an adder and an ALU. They go on to sequential logic, which is like clocked circuits or clocked components. Um, then they go into how a machine language might control that hardware that you build. In machine language, that's just kind of a preview for the assembler thing. So they have their own kind of assembly language that you make. So once you've built those components, you put those all together in their architecture, and now you've got this computer. You build the assembler, and then you move on to higher constructs like a compiler, high-level languages, which are then compiled. So, and then at the end, you build an operating system, and you make a game like Tetris with it. So it's pretty cool. I'm at the computer architecture stage right now. Um, and like I said, their ALU that they make seemed a lot more comprehensive. They are able to do more with it. But just one quick final word on this, or quick view of what you do, how it works. You basically just write in something like C syntax. You define chips. So like this is a 16-bit adder, and it's built off smaller components, which is built here. So you only have the NAND logic gate built in for you, and then you build things like XOR and AND gates and OR gates and NOT, and so on. And then once you build those, then you can use them like it's almost like writing a function. So you're writing like with the C syntax, you're actually specifying a circuit, and then you load it into their software, and it emulates it, it runs it for you. So it's pretty cool. So in this like project 2, they have you build an ALU among other things, and so that's what I have here. They also have a textbook, so I'll just look at it here. So their ALU is pictured here. I'm still only going to do 8-bit inputs, 8-bit numbers. They're doing 16-bit. So they take in two 16-bit values, and then they have a number of control bits that determine what to do with those two inputs, and then they have an output, and then they have a few output bits, like single bits. So that's described here. So you've got two input values, and x and y, and so you've got this zx, which is 0, the x input. So if this is a 1, then you would just sort of substitute whatever x is with all zeros. NX will flip the bits of X, whatever the bits are, it'll flip them. Same for Z, Y, and NY. It will zero or invert those bits. F is, if F is a 1, X and Y are going to be added, and if it's a 0, they're going to be ANDed, a logical bitwise and the result of either of those will be what output is, or out is. And then lastly, there's NO, which flips the bits of output. So that's all kind of summarized here, and then that's what this is sort of the homework of this course. So I defined all the different parts here in this language. They call it HDL, high level, or high description language, hardware description language, I think it is. So so I did that some weeks ago, and I decided that their thing was pretty good. So I was just going to implement this in hardware and make a couple changes to it as well. Here's a kind of a better summary of what their ALU does. So if you know, it's got this whole table of what the various bits can be for ZX, NX, ZY, NY, F, or NO. And the output here for all these different combinations that'll tell you what all you can compute. You can either just get a 0, 1, you can get -1, you can have the output just be X or Y, or the inversion of the bits of X or Y, or whatever X is but negative. You can add 1, subtract 1 to either X or Y, or add them or subtract them. Y from X or X from Y. You can AND them or you can OR them. So their thing can do quite a bit more. I'm going to add something to this to make it so that you're able to check whether or not they're equal, X and Y. But other than that, I think I'm going to just, rather than implement that thing I described earlier, I thought that this seemed a bit more complete. So I'm just going to try to implement this with logic gates in hardware, and kind of scrap that previous idea. So I'll now show a quick schematic that I drew up when I was first trying to solve this. I drew kind of the circuit for how it would be done. So that's another reason I decided to do their ALU. I already, in just doing this homework, I drew up a schematic for it, so I thought it would be easy enough to just wire that up. So I'll show you that. Okay, so before taking a look at the schematic, I just wanted to kind of review the logic gates and their symbols so that when we're looking at the diagram we'll know what we're looking at. We have the AND, that's the symbol for AND. We're gonna get a 1 only when they're X and Y are both 1. This is the symbol for OR. We get a 1 if either or both are 1. So the output for X or Y, you get a 1 most of the time. Only when they're both 0 do you not get that. For NOT, we've got this smaller triangle with a bubble on the end. That just flips the bit of, it takes in 1 rather than 2 inputs. It takes 1 input and flips the bits. There's the XOR. That's going to take the exclusive OR, so only when they're different do you get a 1. If they're the same, whether 0 or 1, you get a 0. And a new component here is a multiplexer, and what that does is take in this case we're taking in just 2 inputs, and we have a select bit, and what it does is basically just kind of pushes through whatever value is coming through X or Y depending on the select bit. So in this case, if select is 0, then the output is just going to be X, and if it's 1, we just get Y. You could have any number of inputs here. You would need more bits to select which one. We're going to be making extensive use of the multiplexer in the circuit. And just to show the ALU again, we're going to have X and Y. And the notation for this too is like, so these are wires basically, right? So this is the an input value X. Here's a wire going into the ALU. It's just kind of black boxed right now. The /8 here means this is actually a bus, eight wires wide. So those are going to be all the bits of X. And then we have that ZX and NX. Those are one bit each. So these are just singular wires. We have ZY and NY. We have 8 wires for Y, and then we have F coming in. I forgot to write that there. 1, 1. So, and NO. So these are control bits. So we have 2 major inputs, X and Y, and the rest are control bits. And then the output is 8 bits, and we have ZR and NG. And I'll talk about what those are. I didn't describe those earlier, but they're going to be just bits that kind of let us know some information about the output. And I added this EQ for equality. It's kind of a control bit that will let us know if X and Y are equal or not. So here's the circuit. What we have here is basically X and Y, and this is 0. So this is 8 wires coming in, and they're all tied to ground. So it's just a low voltage. So one of the things we have to do is invert, or rather zero out X. So, and we do that if the ZX bit is high. So what I'm doing is just sending in all zeros and sending in whatever X is to this multiplexer, and this ZX bit is going to choose which of those to send on, to sort of send forward here. So so then that's going into another multiplexer with itself, with its bits flipped. So the output of this previous multiplexer, whether all zeros or whatever X was, whichever of those gets chosen based on that control bit, ZX, that's going to come out. And what we're going to do is, this is, if you see this dot here, that's just a branch. It's just kind of like we get the same values coming down this wire. But on this branch of it, we're going to flip those bits. So whatever came out of here, we're going to send it on, and we're going to flip the bits, and we're going to send both of those into another multiplexer, and the control bit in X is going to say which of those we choose. If it's a 1, we're gonna choose the version of this that's has its bits flipped and send that on. The same happens for Y. Same logic there. We take in 0 here. So here's 0. It's also coming down to this multiplexer, and Y. The ZY bit controls which one we choose. It goes forward. We split it and flip the bits of one side of it and put that into another multiplexer. And this NY bit says which of those we choose to move on. So these are almost kind of like if statements, If this is true, choose this one. If it's false, choose that one. So we get at this point in the circuit, we have the opportunity to zero out either X and Y, and we've had the chance also to flip the bits of either or both x and y. So then we send we send basically, I mean, from here this is still basically x and y, and we send x and y over to this AND. Again, these are still 8 bits. These aren't singular bits. These are like buses, 8 wires wide. And so this is not one AND gate. It's going to be 8 separate AND gates. It's just easier to draw the one symbol there. And so the output of that is going to be the result, the bitwise AND of x and y. That's here. We do the same with x and y. We send those to the adder. So this is almost, this could possibly be another video. We talked about the adding previously, how you would do that. You would use XOR, you would use an XOR and an and you would basically get the sum and the carry would move on to the next column, and so on. That, I'm just putting a box around all that, but I'll probably make a video on that once I actually start making this, putting this stuff together. So so we're adding x and y there. In this implementation, this NAND2Tetris ALU implementation, if they have an overflow on the final bit, if they have a carry that overflows, goes past, in their case, 16 bits, in my case 8 bits, they just ignore it. So they just let it overflow and do nothing with it. So the AND and the add are both computed, and then this F bit tells us, so we forgot that one there, that F bit tells us which one we want to do. So it's kind of interesting in circuitry like this, they're both being done, it's just which one we sort of conserve. So that's a multiplexer that chooses which of these we want. Once again, we do the same kind of trick where we split that value and send it as it is, and then send it with its bits flipped into a multiplexer. And this is NO. This basically, you know, it flips the bits of the output. So that's just sent out, and that's the output. These other control bits here are for determining whether or not the output is 0 and whether or not it's negative. I don't think I talked about that when we were looking at the textbook for NAND2Tetris, but if out is equal to 0, then that's going to be a 1, and if out is less than 0. So the way this is going to be done is we're going to take all the bits in the number and we're going to OR them. So if we have a string of numbers, ones and zeros, in any given number, we can OR them one by one, and if any one of them is a 1, then the final output is going to be a 1. So basically I'll kind of write that out there. Let's just do a 4-bit number. Let's just do, I think this is this 6? I think this is 6, right? So that would be 1, that's 2, 4, 4 and 2 is 6. Okay, so what we can do, if we want to know, is this number 0, we can just OR this with this and take the result from that and OR it with this and keep going. So if we OR 0 and 1, we get a 1. If we OR that with 1 and this 1, we get a 1. We OR this with this 0, we get a 1. So our answer with ORing all these together is a 1. Only in the case when they're all zeros could you OR them and get a 0. So basically, if we want to know the output is 0, we can just go through every one of these wires and OR them all together. And just because we want our control bits to be 1 if something's true, we can just flip that, right? So if we've got, we OR all these and we get a 0, well, let's just go ahead and flip that to be a 1 because we want this ZR to be 1, meaning yes, it's true, the thing is 0. You could do it either way. That's just the way they do it. So I take every one of these wires, OR them all, and then flip that bit. And then, again, this is 8 bits wide, right? The output. I don't know how, I can't remember how far in depth I went into it in one of the previous videos, but one of the things with binary numbers that can tell you, or the thing that tells you whether or not a number is negative is the most significant bit being 1. So I think I talked about that, where you flip all the bits in a number and add them. So like if we keep with the 4-bit motif here, you can flip all the bits and add 1 to this. So we can flip all those bits and then add 1 to it, and we get 1. So this in 4 bits is -1. So that's always going to be the case, no matter what you wind up with. This most significant bit is always going to be a 1 for a negative number. So what we're doing here is we're just going to take this most significant bit, the basically leftmost or topmost or whatever wire, and that's going to be so it's like, you can think of it like an indexing an array, like the most significant bit of out. You just look at that wire, and if it's a 1, then it's negative. That's this control bit here. So that kind of lets us know, maybe we don't care what it is, we just want to know, is it 0 or is it negative? So I added a little piece to this, which is equality. So what I want to do is, in parallel to all of this, I want to take off X and Y, branch those up, and I want to send them all off onto into an XOR gate, and I want to XOR all of them, and then I want to so take X and Y, XOR them together, then take the result of that and OR each bit of those together. So I'll kind of show what I mean here. So let's say we had 2 numbers which were not equal, like 5 and let's say 2. So what we can do is first XOR all of these. So remember, we get a 1 if they're different, and we get a 0 if they're the same. So those two are different, we're going to get a 1. Those are different, we get a 1. Those are different, we get a 1. Those are the same, we get a 0. Okay, so now what I want to do, that's this step. Notice we still have the same number of bits as each X and Y. I'm going to be doing 8 instead of 4, of course, but so then what I want to do is OR all of those together. That's going to collapse us down to 1 bit. So let's take the output of that and OR all of those. 0 or 1 is 1. ORed with 1 is 1. ORed with 1 is 1. We get a 1. Now I want to flip that. So that's the inverter. That just knots it. And we get a 0. So we got 2 different numbers, and false, they're not equal. Okay, so let's show how this would work with 2. Let's just do 5 and 5. So if they're the same, we get a 0 with XOR. So that's going to be 0, that's 0, that's 0, that's 0. Then we OR all of them, that's 0. Then we knot that, and we get a 1. Yes, it's true, they're equal. So So that's basically what this part of the circuit is doing. We're going to XOR each one, and if any one of these, you know, if you had numbers where, you know, they were like all the same except one bit, you know, you would get 0 0 0 in the XOR, and you get 1 1. So if you have even just one where they're different, you're going to get a 1 in the XOR, and then you're going to OR all those, and that 1's going to persist through, and you're going to get a false for equality. So that's a quick overview there of the circuit, and I have pretty much received all of my stuff. So I got a bunch of these boards that I can use. Some more of those. And then these are the chips I got. So I've got a lot of different chips here set up. Maybe I'll make a video about this one. This is going to be different. This is something else here, but so yeah, those are all the chips I got. Usually about 50 cents a piece, so that it's not too costly to do all this. I'm kind of worried about running out of the multiplexers. Actually, I only have 10 of them, and I think they are 8 bits each or something like that. We gotta look at the sheet for that, but I'm not so sure I'm gonna have enough, because I might have to do 8 of these. Like, it might take 8 of these chips just to do one selection. So I'm not sure. I might look into a different chip, maybe even. And this is an interesting chip here. This is a timer. It uses a capacitor that takes a little bit of time to fill up with charge. And so assuming I got this ALU working, I could then maybe do something with a timer and have, you know, kind of make a loop which would continually, like, maybe take in values from registers and compute stuff with it, and you could kind of get this sequential timed thing going on. But anyways, I'll end it there. I think this is going to be almost a 30-minute video. So I'll let you know. I'll make a video when I start actually building stuff. See ya. Bye.